Hi everyone, welcome to my talk. And I am Hongzheng, currently a third-year PhD student at Cornell, supervised by Professor Zhiru Zhang. And today I'm going to talk about our work on Allo, a programming model for composable accelerator design. And this work is in collaboration with Niansong, Shaojie from Cornell, and Zhichen and Mengjia from USTC, who were also interned at Cornell. So over the past 2 years, we have witnessed the size of deep learning models grow exponentially. In order to satisfy the increasing computation demands, many researchers and companies turn to specialized hardware accelerators to accelerate those applications. However, accelerator designs is quite different from programming on general processors. It requires users to manually handle the custom processing engines, custom memory hierarchy, and custom data communication, which is far more complicated than general programming. The first challenge of designing high-performance accelerator is to balance manual control and compiler optimization. Here, I show a code snippet of matrix multiplication written in C++ high-level synthesis. And we can see that even with the help of HS, the code is still very complicated. Starting from a vanilla MapMal kernel, we may add compute customizations like loop tiling, loop unloading, and pipelining, which requires manually rewriting the loops. Furthermore, we may also include custom memory hierarchy by creating intermediate buffers and conducting memory partitioning. So lots of pragmas and I/O logics will be inserted in the original code. Lastly, we may also incorporate data movement optimization. It requires programmers to restructure the code into multiple pipeline stages and connect them using FIFOs. From this example, we can see that it may take about 500 lines of HS code, even for a small systolic array. And this approach is vendor-specific, hard to maintain, and not able to reuse across different applications. Existing high-level synthesis compilers like ScaleHS attempt to tackle this problem to provide automatic design space exploration. However, since it only considers the compute customizations, the overall performance is still far from the optimal manual design. Therefore, to tackle these challenges, we propose Allo, an accelerator design language and compiler. Allo is the preface of Allo solvers, meaning different kinds of hardware. We make several design principles for our programming language. The first one is Pythonic. Since nowadays Python is the most popular programming language for deep learning and data analysis, a Python embedded language is more acceptable by programmers. As shown on the right, users can firstly define an Allo kernel in Python using a basic three-level nested for loops to calculate the matrix multiplication of C equal to A times B. We support freeform imperative programming and support Python native keywords. So users do not need to learn a new DSL, but can easily write a Python program as usual. The only difference is that users need to explicitly provide the type annotation, which will be used to infer the bit width of the actual hardware modules. On the contrary, the previous DSLs like TVM tensor expressions use a declarative way to write a program, which is not straightforward and it's hard to express control flow that is very common in hardware accelerators. To ensure productivity and maintenance of hardware designs, Allo also inherits the idea of highlight and TVM by separation of concerns. Allo does not only decouple the compute customizations, but also decouples memory and communication customizations from the algorithm, which enables more complicated optimizations. In the middle end, we use MLR as the intermediate representation. Different from TVM that use a monolithic lowering approach, Allo enables stepwise verified revise. So users can immediately print out the transform module after applying each primitive to inspect whether the customization is expected. In the following, I will use an example of transforming a gem kernel to systolic array to demonstrate how to write a program in Allo. After users define an algorithm in our front-end language, we can create a schedule by calling allo.customize. A schedule here is a sequence of customization primitives. We can see from the architectural diagram on the right, the default implementation only has one PE and reads data from A and B tensors and write back to C. After creating the initial schedule, users can apply schedule primitives to customize the hardware design. For example, buffer add is to create intermediate buffers between the PE and the input arrays. And unfold can explicitly unfold the loops into multiple hardware processing engines. Partition is the memory customization that creates more memory banks along specific dimension for parallel memory access. And relay is the communication customizations that connects the buffer with PEs using FIFOs. Finally, we can achieve this output stationary systolic array. From this process, we can see only a line of schedule code is needed, which greatly simplifies the programming burdens to construct a complicated systolic array. To test whether the results are correct, we can lower the code to the CPU backend and leverage our LVM execution engine to run the optimized module. However, the CPU simulation cannot easily identify bugs like deadlocks in a data flow design, and we need a stronger guarantee for those customizations. Therefore, we integrate a formal equivalence checker that we propose in the FBJ24 paper to formally verify the equivalence of the vanilla module and the transformed module. The verifier uses a symbolic execution and can quickly support statically interpretable control flow and verify large designs very quickly. After we make sure the design is correct, we can finally push the design to the HS backend to do the hardware synthesis. And we can see that Allo-generated systolic array can achieve the same performance of the state-of-the-art systolic array generator AutoSA, but with much lower resource usage. Moreover, our customization primitives are expressive enough to construct different data flow architecture. Compared to previous approach that leveraged space-time transform to generate systolic array, Allo provides an easy way for users to quickly change the size and the configurations of this different systolic array with minimal schedule code. Now, suppose we have already optimized the single kernels. The question becomes how we can compose those kernels into a functionally correct and high-performance accelerator. Here, we showed an example of cascading two MATML kernels, which is very common in nowadays transformer-based language models. We propose a compose primitive that allows users to incorporate the previous defined schedule to the top-level function. However, simple composition is not enough. Just like playing a puzzle, not all the pieces can be matched perfectly, and we need to find the right piece and connect them together. Specifically, if the output argument of the intermediate buffer of the first kernel is partitioned along the 0 dimension, then the input of the second kernel should also be partitioned along the same dimension. Otherwise, the interface mismatch, and the kernels cannot be connected together. So the goal here is to model the function arguments in both callers and callees, and to make sure the function interface or the layouts are the same. To maintain the argument information of both callers and callees, we construct a hierarchical data flow graph, where each node contains the name of the variable and the function that the variable resides. Then, in this case, we need to guarantee the 3 nodes in the red box have the same layout. This is exactly what type checking does. Therefore, the key idea is that we can model the data layout as a type. We have 4 base types. Bottom means complete partition, top means no partition, and C alpha means cyclic partition with a factor of alpha, and B alpha means bulk partition. And then we construct a subtyping relation between these base types. Basically, we want to make sure we always provide more read or write parallelism for the variables, so the kernels can always be executed correctly. For example, if a kernel accepts an argument without memory partition, then if we provide a fully partitioned variables into it, then the kernel still can run. Therefore, we have these 2 subtyping relations. And actually, this subtyping relation forms a lattice, which provides a very good property for our inference algorithm. So the data layout propagation problem just becomes the type inference problem in this type system. To make sure the global consistency, we leverage the worklist algorithm to infer the types. Since our problem has a very good lattice structure, so the inference algorithm is very efficient and can converge in linear time. The formal proofs can be found in our supplemental material. For the experiment, we first conduct a single kernel evaluation. We take the designs from the polybench benchmark and compare Allo with other baseline systems, including the basic Vitis HS, 3 accelerator design languages, HeteroCL, Dahlia, and Pylog. There are also 2 automatic HS compilers, Scale HS and Merlin, that leverage automated design space exploration to generate hardware designs. And we can see from this figure, Allo can always achieve the best performance in these designs with orders of magnitude better than the baselines. This is mainly because Allo has sophisticated memory and communication customizations that create efficient memory hierarchy and data placement schemes. This experiment also proves that only searching the compute customization using DSC is still far from optimal. Apart from latency, we also conduct analysis on the resource usage of those designs. Compared to the state-of-the-art HS compiler Scale HS, Allo achieved lower latency by reducing the initialization interval to 1. Since the design is better pipelined, we also achieve a higher place and route frequency. To demonstrate the scalability of Allo, we also conduct multi-kernel evaluation by constructing a complete LLM accelerator. We take the context GPT-2 model and create a fully pipelined data flow design for this model. In Allo, since we have already optimized the kernels, we can directly compose each submodule together to form a complete design. We mapped the design on an AMD U280 FPGA running at 250 MHz and evaluated the design in a single batch, low latency generated inference setting. Compared to the previous overlay design DFS, we can achieve a 2.2 speedup in a preview stage. Even compared to the A100 GPU, our accelerator can still achieve a better performance and much higher energy efficiency for long output sequence. And most importantly, we can achieve this amazing performance in Allo with less than 15 lines of scheduled code. To further make our design more accessible to other researchers, we also encapsulate those neural network operators into a library and integrate Allo as a backend compiler of PyTorch 2.0. So users can directly import the PyTorch model and generate the optimized accelerator design in a push-button way. To sum up, we propose Allo, a Python-embedded accelerator design language that is able to generate a large-scale accelerator in a productive way. In the future, we will also target other backends like ASIC and MPU, and try to include more automations in Allo to further reduce the programming burdens of writing a schedule. Also, sparsity support will be incorporated in our framework in the future. Our code and artifacts are open source. Please feel free to take a look. And that's all of my talk today. Thank you, and I'm happy to take any questions.
We've got time for a question or two. Any questions? Can you please state your name and affiliation when you ask your question? Thanks.
Nice talk. I'm Zhang from Seoul National University. So I guess the FPGAs have limited memory, so you'd likely have to distribute your model among different FPGAs. Do you have any support for that?
Yeah, so our group is currently working on that. So currently, for this PLDI work, we only target a single FPGA device. But actually, in our other paper that was published in FCCM24, we discussed the possibility of scaling the accelerator to multiple FPGAs. And you can refer to our papers. And we are also working on that.
Thank you.
Hi, May Milano, Princeton University. You have a subtyping scheme where you're able to infer types.
Yeah.
Are you inferring principal types?
What do you mean by principal type?
Is there a notion of a most specific type for everything, and does your inference algorithm find that most specific type?
Yeah, so basically we try to unify the layouts. So if the memory layouts of two kernels are not the same, we try to find the least common value on the lattice and try to unify them. So you can refer to our papers for more details.
Thanks.
Okay, I think we're running right on schedule, so we might go to the next talk. So thank you, Hongzheng.
Yeah, thanks.